We know the laws of physics are universal in nature. We know the laws of chemistry are testable, and we have established their applicability out there in the cosmos. But there is one science that has never been tested before because we don't have an example elsewhere. That's biology, right? Establishing life elsewhere would give us that laboratory to understand how do biological mechanisms work at a fundamental level universally. I'm Nikku Madhusudhan. I'm a professor of astrophysics and exoplanetary science at the Institute of Astronomy at the University of Cambridge. Yeah, how do we narrow down which planets to look at in the search for life elsewhere, right? So today we have over 6,000 exoplanets out there. These are planets orbiting other stars. So how do we know which planets to look at? So most of the time the path is observationally driven. There are two aspects. First, you want to understand which of those planets could be potentially habitable, theoretically speaking. In other words, there are some loose definitions, like the habitable zone, for example, is the planet at the right distance from the star to have the right temperature, global temperature that could allow liquid water on the surface. Now, for that to also happen, you also need that the planet is small enough that it could have liquid water on the surface, right? So the planet has to be small enough. Earth-like planets are very good targets because we know one example that works. But you could also be the planet could also be slightly larger than Earth and could still have a surface. But at that point, the more important bit is it at the right distance from the star, and is it the right kind of star, and so on. So you want to narrow that down theoretically first, and then you need the observational considerations, which is the planet could be in the habitable zone, but if the star-planet system is very far from us, our telescopes won't be able to detect the atmospheric signatures of those planets. They'll be too faint. So the planet-star system has also to be close enough that we can detect their atmospheric signatures. So it's this combination of theoretical considerations and observational considerations that allow us to select which planets to look at. And to give you a rough estimate, today we know of less than 10 planets. Think about it, of these over 6,000 exoplanets, we know of less than about 10 planets that we can look at with our current facility, even as big as the James Webb Space Telescope is. That's all we've got. Maybe we can increase it by a few, but it's not a lot more. So that is where all our resources are going into in the search for life. Once you have established which planet to look at, then the next step is to conduct observations of the atmosphere of the planet. For that, certain other conditions need to be satisfied. The planet has to be in the right orbital geometry and so on. But that is the next step, is to conduct atmospheric observations from which we can determine the atmospheric composition of the planet. And in that atmospheric composition, we are looking for molecules that could be indicative of life on the planet. And that's what is referred to as biosignatures. So these are molecules that would be released by life on the surface of the planet. And then that comes into the atmosphere, where then it becomes observable from spectroscopic observations. So what is transmission spectroscopy? One way to observe the atmosphere of an exoplanet is if the planet is in what is known as a transit geometry. That is, when you're looking at the star, the orbit of the planet is inclined in such a way that the planet passes in front of the star as seen from the observer. So when that happens, some of that starlight passes through the atmosphere of the planet before reaching you, the observer. And in that process, what happens is that some of that starlight is absorbed by molecules in the atmosphere of the planet. So if you're looking at a stellar spectrum, when the planet is going in front of the star, some parts of the stellar spectrum at some wavelengths are absorbed more than others. So that relative measure gives you an indication. It's basically a fingerprint of the molecules that are in the atmosphere that are causing that absorption. So today we have these tools called atmospheric retrieval tools, which take that absorption profile, we call it a transmission spectrum, absorption as a function of wavelength. We can take that spectrum and invert it to get what is the atmospheric composition of the planet. Yeah, so the planet K218b is one of the best targets in the search for life currently. So the planet was discovered just about 10 years ago, The planet is about 9 times Earth mass and about 2.5 times Earth size. So if you ask someone 5-6 years ago, would this planet be habitable? Most people would say no, me included. The planet is in the habitable zone of its host star, which means it is close enough to its host star that if you had an Earth-like planet in its place, it could be habitable. It could have liquid water oceans on the surface. However, this planet is too big. So 5-6 years ago, there was the common notion that a planet that we could never be habitable. We would call that a smaller version of Neptune with pressure and temperature too high at the surface. However, what happened is about 5 years ago, actually, we looked at this planet in more detail. We tried to understand what are the various possibilities for its interior composition given its bulk density and the fact that we had a good guess that its atmosphere was probably hydrogen rich based on Hubble observations with the Hubble Space Telescope at the time. So we came up with a prediction that if the atmosphere is hydrogen rich, there is a small space of solutions in the entire parameter space of internal structure models of the planet. There is a small region of that parameter space which does allow for liquid water on the surface. If the atmosphere is just thin enough, we are talking about few bars to few tens of bars worth of an atmosphere, a hydrogen-rich atmosphere. We established theoretically that it could in principle have a liquid water ocean on the surface. And that is what set us on this path, saying, well, if there is a slight chance of it being habitable, we should look. And then we started looking, and that's the story of what we have been doing in the last 5 years with JWST, with atmospheric observations of this planet with the James Webb Space Telescope and more theoretical work. And it is looking currently that the planet could indeed be habitable. So it has come to the forefront of exoplanet science today as one of the best locations to search for habitability and potentially life. So what is a Hycean planet? So K2-18b serves as the prototype for that. So about 4 to 5 years ago, we conducted this exploration, again a theoretical study, to understand how big, both in how large in mass, how big in size, and what temperatures, stellar types, and so on. What is the range of planetary properties, system properties that could allow for a liquid water surface ocean and a hydrogen-rich atmosphere on a planet like K2-18b. And we found that indeed there was a large region of parameter space, and we called those planets Hycean worlds. The word Hycean stands for hydrogen and ocean. So these would be planets that would have liquid water surface oceans, surfaces entirely covered in oceans, and a hydrogen-rich atmosphere. So there won't be any landmass on this planet. So effectively these are ocean worlds, but with hydrogen-rich atmospheres. What is the relevance of K2-18b in the context of Hycean worlds? It's because this was the first candidate Hycean world for which we made atmospheric observations with the James Webb Space Telescope, and we found carbon-bearing molecules for the first time ever. These are methane and carbon dioxide at high abundances. And we didn't find other molecules like ammonia and water vapor and carbon monoxide. So this combination of chemicals that we found or not found was already predicted before making the observations as indicative of a Hycean world. So that was a major triumph, a congruence of a theoretical prediction and an observation that came about from the JWST observations and took us one step further in thinking that maybe this is actually a Hycean world. So there is still a lot of theory and theoretical debates that are happening in the field on whether we can robustly establish that. But there was one other clue, which was this molecule, dimethyl sulfide, for which we found a very, very feeble tentative hint in 2023 in the near-infrared observations. DMS is a biomarker here on Earth, so it's predominantly produced by life here on Earth and had been predicted for almost 20 years now as one molecule that you should look for in the search for life elsewhere. On Earth, this molecule is produced primarily by microbial life, phytoplankton especially. So when we found it, we had predicted this for K2-18b as well if it was a Hycean world. So when we found it, that was a major moment in demonstrating the capability of detecting biosignatures. So the biosignature itself wasn't robust. It was just a tentative hint, but it told us that we could in principle detect it. Then we went back in 2025, earlier this year. So last year we made the observations in 2024, and we published this year the first mid-infrared spectrum of a habitable zone planet, a candidate Hycean world ever. That's K218b, and we found also tentative signatures of dimethyl sulfide. So again, the signal is tentative, and there are possible degeneracies with other molecules like dimethyl disulfide, for example. But what we are establishing are tentative hints in multiple wavelength ranges that we are seeing evidence for that same molecule. So that could be a biosignature, but we are also looking at other non-biological explanations for that molecule. So it's a very exciting time to be even considering the possibility of life, even though we can't confirm right now that we have definitively detected life. It's a very pertinent question at this point in time to ask, well, suppose K218b is actually inhabited, right? Suppose DMS signal is real and that there is life. What would the environment look like? What would life there look like? Now, it is, I have to admit at the very outset that it's very hard to speculate. We simply don't know of any such planets in the solar system. There are no Hycean worlds, right? We don't know what such planets would be like. We don't know what evolution would be like. We don't know what life forms there would be like. We can only speculate. So our bare minimum assumption is that of microbial life. So we are, when you see a strong signal of DMS, if we can confirm that, our hypothesis is that there's got to be a lot of microbial life of the kind or a variant of what we see here on Earth, which also produces a lot of DMS. That's where most of DMS on Earth comes from. So that's our baseline assumption. Now, beyond that, as to whether there can be complex life on this planet, we simply don't know. Right? So even on Earth, there are a lot of unknowns about how life came about, so we can't speculate. But it's anyone's imagination. You have an ocean, and you have the seed of life, and you have the microbial life form. From there on, there are endless possibilities for what life can be like, but it will be not very prudent on us right now to speculate the exact nature of life. We'll be getting ahead of ourselves. At this point, we should just try to establish if the atmospheric signature is real in the first place, is robust, and then we work our way towards more complex questions.